Good morning, everyone. Let's start today's seminar. So originally, we planned to do the seminar in the hybrid way, in offline in the KIAS seminar room, and but yesterday there was a single case at the building number 8, and Songmook was using the building number 8, so he got a PCR test last night, so we just change it to do it online. So Songmook is now visiting KIAS, and he is from Yonsei University under the supervision of Professor Songchan Park. And today we're going to talk about reheating prediction and the phenomenology from inflation with non-minimal coupling. Please start, Songmook.
Yeah, thank you very much for the introduction. So yeah, as Dong said, I'm now working in KIAS, and I actually from Yonsei University and working with Songchan Park. And yeah, unfortunately, I'm very sorry about I was expected to give you a hybrid seminar in offline, but now I'm getting a negative results in this morning. So yeah, I will also visit KIAS from Monday next week. So yeah, feel free to contact me. So today I want to talk about the reheating predictions and phenomenology from inflationary models with non-minimal coupling, and this is based on work with 2 papers with Songchan Park and Kinya Ora and Donghyun Chung. And please feel free to interrupt me anytime whenever you have something unclear from me. So in this talk, I want to first give you an introduction of the motivations why we study the reheating processes more carefully, and also give you some basic procedure of particle production during the reheating as well. And I divided the talk into the 2 parts, and first part is about the reheating in models with non-minimal coupling. And here, actually, the reheating processes actually changes the predictions of inflationary models, and this part can be done a little more model independently. And I will give you some general templates for NSR and R plots for general classes of model, like non-minimal coupling inflation. And in part 2, I will turn my gears to a slightly model specific part. In spontaneous leptogenesis from Higgs inflation, I will give you an example of some close connection to BSM physics and reheating processes. And I will conclude. So yeah, let's begin with the introduction. So now the inflationary paradigm is a part of standard history of our cosmological model. So by having some exponential expansion at the early universe, we can solve the horizon problem and flatness problems. And in some model, if you are serious with gods, we can eliminate some unwanted relics as well. And more importantly, it is known that the initial quantum fluctuation can be larger during the inflation and can be seized for larger scale structure, and also may explain the CMB anisotropy as well. But on the other hand, the detailed reheating process, which means the transition from the end of the inflation to the summer universe, is usually overlooked. Practically, this is due to the theorem proved by Weinberg, because if this larger scale structure or structure formation is coming merely from the quantum fluctuation during the inflation, the conservation of the curvature power spectrum at the super horizon guarantees us that we do not need any details of the reheating processes to have some predictions for this regime. But on the other hand, another reason may be the non-linearity and non-perturbativity and model dependence of the reheating processes itself. So yeah, I will explain this second part more, because it may be relevant for the rest of my talk as well. So after the inflation, inflaton starts to oscillate near the origin of the fields, and it starts to coherently oscillating and starts to decay to standard model particles, or may probably to dark matter as well. And here with some decreasing envelope, it shows some sinusoidal oscillations. This decreasing is due to the Hubble expansion. So elementary theory of the rating is first rather perturbative, and phenomenologically it is described by introducing this friction term coming from the decay rates of the inflaton fields to other particles, and rating completes when these decay rates of inflaton become comparable to the Hubble rates after the inflation, by losing its all energies to radiations. But in this model of theory of the rating have many missing parts. One major point is that inflaton is not a single particle, but condensates, which consists of infinite number of particles. So we have to consider these effects. And also, as the particle is produced, it will back react to dynamics of the inflaton itself. And so we have to consider this back reaction effect as well. So to explain these parts, the first part, I mean, the effects from this condensation, more explicitly, I will introduce some toy model. So here, with this usual inflation model, single field inflaton Lagrangian, we will consider this coupling between inflaton and chi field, which will be called daughter particles. This will give you effective mass for chi field, even if it is initially massless, it is effectively became time-dependent mass. So this is very well-known problem of harmonic oscillators with time-dependent mass. So it is also known that there are various types of resonances happening, like narrow resonances or broader resonances, depending on the parameters like coupling G, or the amplitudes of large phi, or mass of the inflaton m. So in the light panel, you can see the number of chi field exponentially increasing gradually. But this once I consider the expansion of the universe as well, this exponential increase of the number density became weaker than before. So it, in the end, it will converge to some certain values. But before that, by having such a large number of chi field, we have to consider the back reaction. So at late time results is become unreliable. So this kind of non-perturbative particle creation can be considered in some little bit different aspects. So here, by having some mode expansion for chi field with some positive frequency modes and negative frequency modes, initially this chi field is have this positive frequency modes at first, with alpha coefficients to be 1 and beta coefficients to be 0. But in other picture, it can be understood as some transition of the vacuum states. So here, this out vacuum states and in vacuum states is defined with these different annihilation operators and creation operators, which are connected with these Bohr coefficients, alpha and beta. So here, by having some time-dependent mass system, it is basically like having some external time-dependent external source. So even if these in vacuum states are defined to be the states with a 0 number, the same in states with a different definition of the vacuum with out states is understood states with some finite number, which is parameterized by beta squared. So non-zero beta corresponds to particle production. So here, now compared to elementary theory of the reheating stages, now we have some more complicated picture of reheating stages. So at first we have some non-perturbative preheating stages, which shows some resonance behavior. And after that, due to the back reaction of the produced particle, this preheating turns off. And then we have to move the elementary theory of perturbative reheating by pure decays of inflaton. And then we also have two very nonlinear and complicated processes of the summarization. So even if it is the overuse of the words, we define this whole procedure as a reheating, also in my talk as well. So as you may notice, it is a very still non-linear and non-perturbative. So in general, some analytic understanding has its own limitations in general. So generally, we have to rely on some numerical simulation. So in the light panel, I prepare some usual results from the numerical simulation. This is for the Higgs inflation model, and this shows the evolution of the equation of states during the reheating. So it starts from 0 values, and it converges to 1/3 LA time gradually. And okay, even if this is a kind of complexity of the reheating stages, and even if we do not need any detailed physics of the reheating to have some solid predictions for NSNR, why do we still care about the reheating? So here I will give you two motivations. So first one is about the conceptual reason. Basically, reheating processes provides the initial conditions of our summer Big Bang. So in this inflationary paradigm, now the beginning of the summer universe is not a something like explosive explosion, but not a explosion, but just a smooth transition from the after the inflation to summer Big Bang by smooth the decay of the inflaton fields. So in this sense, it is quite natural to ask if, for example, dark matter can be produced during this decay of the inflaton, or if the baryogenesis can be realized during this reheating processes without large washout effects. So even if it is quite model specific, there are, depending on model, it shows very rich phenomenology connection to VSM physics. And also in some models like Coverton scenarios or modulated reheating, even the original primordial fluctuation explains the CMB anisotropy is not coming from the inflaton, but coming from the decay of some other particles like Coverton during the reheating as well. So I will deal with some aspects of this, especially for baryogenesis in part 2 of my talk. And also I want to emphasize there also some practical reason of studying reheating more carefully, in a sense that reheating really changes the predictions of the inflationary models. So here, this aspect is become more and more important in this era of precision cosmology. So when you open a paper given by the Planck, they just give predictions for NSNR for defaulting number to be 50 to 60. And my claim is that this is too naive, because this 60 and 50 voting just accounts some uncertainties coming from the reheating processes, but we can do better by parameterizing some parameters during the reheating stages. So this part can be done less model dependently, because we can classify some models of the inflation. So here, this part I will cover this one in part 1 first. So this is the end of the introduction. So I wonder if there is any questions or comments in this introduction part. So if not, I will move to part 1 about the rating in models with non-minimal coupling. So rating parameters, the rating stages can be parameterized with some numbers. So first one is the e-folding number during the rating. And the second one is the equation of states during the rating. But here I only need this averaged value of the equation of states. And also the rating temperature is defined the temperature at the end of the rating. So in principle, if you have some real-time evolution of equation of states during the rating, as we obtained from the numerical simulation, you have all these informations as a whole. But even if we do not have such a numerical results, we can parameterize, phenomenologically parameterize. So when you see these expressions for the e-folding number, this 61.6 corresponds to like e-folding number we need for instantaneous rating when and rating to be 0. But if we have some prolonged rating stages with some effective equation of states different from 1/3, it will reduce the required number of nk, and k is the e-folding number purely during the inflation, and becomes smaller and smaller. And in light panel, it is quite easy to understand how rating really changes the inflation predictions. So here, e-folding number corresponds to horizontal ranks of during the rating, and this equation of states determines the slope of this figure. So this red line corresponds to, this orange line corresponds to size of the cosmological horizon, and this blue line is evolution of the corresponds to CMB multiple CMB pivot scale. So by having different slope and different horizontal region, it really changes the timing when the CMB pivot scale leaves this cosmological horizon, denoted by this yellow circle. So in this talk, I will focus on inflation with non-minimal coupling. So from the observation already, many models of inflation is being disfavored, like all polynomial types are already being disfavored. And also recent biset results tightens the upper bounds of the tensor to scalar ratio as well. So, and this R power tractor type and R square inflation enjoys the sweet spot of the Planck observation. So this kind of suppressed tensor to scalar ratio requires asymptotically flat potential with a Sifert symmetry of the inflaton. So this is not required by the inflation itself, because even if we have some polynomial type of inflation really happens. But this is quite observationally disfavored. So non-minimal coupling, introducing the non-minimal coupling between inflaton and the scalar is one way to realize this asymptotically flatness of the potential, and also covers a wide range of models. And this is all called the behavior of R power tractor behavior. So for example, Higgs inflation and Stravinsky inflation, after we define some fields and eliminating R square term and turn into scalar tensor theory, or even some multi-field inflation like Higgs R square inflation, even if it is multi-field inflation after integrating out some heavy modes, this wider range of parameters shows that a single field like behavior for this model, and even these kind of models can be considered as effectively single field inflation with non-minimal coupling. And also equivalently importantly, so reheating really breaks the degeneracy of these classical equivalent theories. So for example, Higgs inflation and Stravinsky inflation, as I said, equivalent classically, but these two types of models really have different types of interactions to standard model particles and possibly to dark matter. So they will have a different history of the reheating and gives different predictions for inflationary predictions as well. So it can be used as a kind of proof of microscopic physics, which determines the coupling between inflaton to other sector. So here from the Jordan frame with the non-minimal coupling K to reach scalar R, by doing some field redefinition, we can go to Einstein frame without any non-minimal coupling, but with a transformed kinetic term and the potential. So in potential term, we have additional 1 over omega fourth vector in the Einstein frame, and also have some non-canonical kinetic term. So here, this zeta parameter shows the difference coming from different formulation of the gravity. So actually, in extended gravity series, there are two formulations of gravity. So the first one is a metric. So in this metric formulation, the affine connection is given by the Christopher symbol, as usual as we learned in pure GR courses. But there are another way to formulate the gravity, which is called the Palatini formulation. So here, the affine connection is priori independent to metric, and these relations are given by the equation of motion. They are equivalent at pure Einstein Hilbert action level, but really gives a different in modified one like FR gravities or inflation with non-minimal couplings as well. So we will consider both formalism. And coming back to this non-minimal coupling cases, from this effective transformed potential form, we can lead of the condition for asymptotically flatness. So here, V over K square at large field values should be converges to some certain values, positive values. So here we will consider the monomial functions for K and V. So here you can see this monomial function satisfies the condition for this asymptotically flatness. And even if we consider only monomial functions, it is quite straightforward to generalize to arbitrary cases as well. So here's the results. So to be explicit, I will explain M equal 2 cases with the metric case. So here at the most light size, the black borderline corresponds to W to be 1/3, which corresponds to radiation like dominant universe. Or this prediction, because there is no difference between the heating stages and radiation dominant universe, because it shares the same number of the equation of states, the predictions are the same as instantaneous reheating, with the maximum temperature to be order of 10 to the 15 GeV. But once we depart from this W to be 1/3, depending on reheating temperature, it gives different predictions for inflation. So here, for this metadominant-like universe, we present the predictions from inflation for different temperatures. So for example, this 10 to the minus 2 GeV corresponds to BBN scale, and which can be regarded as lower limits for possible reheating temperature, is already disfavored in this W to be 0 case. We also plot the predictions for 10 to the 5 GeV corresponding to main target of future collider, and also we consider 10 to the 10 GeV. So this is an example of, this is the reason of gravity no overproduction problem is considered in many SUJI models. So once you have larger temperature than 10 to the 10 GeV, order of 10 to the 10 GeV, maybe the gravitino is overproduced, so overcloses the universe. So it is called the gravitino overproduction problem. So by having some specific models and such a specific statement also have some indications for the predictions of NSM parameters in this template as well, by having some upper bounds of the reheating temperature. So this brown line corresponding to W to be 1/5, this is some values between 0 and 1/3. So now you can see these possible predicted parameter regions from reheating is become narrower and narrower, and being closer to, and reheating dependence become weaker. So in this paper, we showed all the templates for m equal 1, 2, and 3, and 4 cases. And I want to note that in such a large values of m, even a minuscule values of psi, like 10 to the 2, 10 to the minus 2, or 10 to the minus 3, is also can be within the current Planck and bicep bounds of NSNR. And also this purple region and the blue region corresponds to expected future experiments like CMBS4. And depending on is now if the CMBS4 is giving constraints of R smaller than 10 to the minus 3, it may rule out all the models of inflation with non-minimal coupling in metric cases. And either way gives some certain values, which will further constrain this NSNR and also reheating temperatures as well. So also I will talk about the Palatini cases. In Palatini cases, when m is larger than 3, and all the results are already ruled out by Planck. So here I only present the cases for m equal 1 and 2. And especially for m equal 2 cases, it can be considered as a Higgs inflation in Palatini case. So having some lambda values to be 10 to the minus 2, we have to assume larger non-minimal coupling to be 10 to the 8 in Palatini formalism. And you can see here, it is already at the edge of the 2 sigma bounds of Planck and bicep measurements, even in the cases of instantaneous reheating. So further observational improvements will constrain this model. So usually consider 60 and 50 folding doesn't give us such an indication because it just becomes straight line directly down to smaller, very large suppressed test to scalar ratio. So by considering the reheating processes, we have some indication for this Palatini cases and may constrain this model by constraints from NS rather than R. So I will give you a brief summary of part 1. So reheating stages changes the inflationary predictions. And then we provide some general templates for inflationary predictions considering reheating processes in metric and Palatini formalism with general monomial potential. And we consider the wider range of non-minimal coupling, even if it is smaller than 1. For some monomial potential, it still explains the current NSR values. And future constraints on NSR will rule out the models or at least constrain the reheating temperatures as well. So this is the end of the part 1. So I wonder if there is any comments or questions so far. If no, let me move on to part 2. I have 10 minutes. So in part 2, I want to my gears on more model specific parts, but which really shows a direct connection to VSM physics, especially baryogenesis. So here we all know that there is some baryon symmetry in our universe, and the ratio between the baryon and photon number is given by order of 10 to the minus 9. And now this it is well constrained from CMB and BBN. And this magic number is known to be very hard to explain solely within the standard model. So usually the conditions for this baryon symmetry is summarized by Sakharov conditions by having some baryon number violation and CNCP violation and out of equilibrium. But in this talk, I will replace this baryon number violation to lepton number violation, as usual in leptogenesis scenario, by introducing some dimension 5 Weinberg operators. And this CP violation also will be replaced to a spontaneous CPT violation by considering some higher dimension operators. It will induce the effective chemical potential. And because we are basically considering the reheating stages, the out of equilibrium is automatically guaranteed because we are not in the summer equilibrium. The idea of this spontaneous CPT violation is not something new. So in 1980, already Cohen and Kaplan suggested a model called the spontaneous baryogenesis. So original idea was to consider the specially homogeneous configuration of Goldstone boson excited during the inflation. And by having this specially homogeneous configuration, we spontaneously breaks Lorentz symmetry. And it turned out that it may induce effective chemical potential between particle and antiparticle and baryon and antibaryon. So even after the inflation, by having some velocity of this Goldstone boson, due to its decay products from the inflaton to a summer background, even in the summer equilibrium, it is known that it may give some finite number of baryon, and it is called the Hahn-Bizum of this spontaneous baryogenesis. But after that, it is also known that even perturbative and non-perturbative decays during this oscillation of the Goldstone boson may give enough number of the baryon symmetry, but it is known that the number density is usually too small to explain the current Rayleigh of the baryon. And possible extension of this cases using standard model Higgs was first considered by Kosenko in 14 and 15. But the point is that this kind of fast oscillation is always naturally realized during the reheating after the inflation, and this kind of Lorentz symmetry and CPT violation is a generic feature of once we have inflationary phases at first, because we have some free-fall time direction. So here I want to be more specific to consider the model of Higgs inflation. This corresponds to M equal 2 and metric cases in part 1. And this we have by having some non-minimal coupling, even if this chaotic type of Higgs potential may explain the current gives the best fit to Planck regions. And this is interesting possibilities because this is the really only candidate of the inflaton of the standard model. So one unique feature of this Higgs inflation is that all the standard model fermions and gauge boson couplings are already known, and these are also become time dependent due to its oscillating vacuum expectation values of Higgs. And this feature will be very essential in my consideration. And yeah, let's focus on slightly different perspectives. So the renormalization group program told us that actually standard model should be considered as an effective field theory, instead of being a usually completion. So in this kind of feature, we can have a large number of irrelevant operators at high order. But during the inflation, different from the low energy, these irrelevant operators may have some very important roles because we have a large field values, basically. And sometimes this induces very severe theoretical problems of inflation, because this also induces a large mass for inflaton. And we usually do not have protected symmetry to prohibit such a mass generation of the inflaton at large field. But here I will only consider the reheating stages and only Planck suppressed symmetry breaking operators. So in this sense, the following consideration can be regarded as a minimal and intrinsic amount of retinal symmetry generated from the Higgs inflation. So here first, to realize the retinal number violation, I will introduce the dimension 5 operators as I advertised. And due to its Planck suppression, so there won't be a large washout at late times. And also, I will consider the dimension 6 operators, which is similar to the coupling of a usual spontaneous baryogenesis scenario. Here, I consider the lepton current. Even if you have a coupling to baryon current, we do not have an explicit baryon number violation. This does not have any loss of the contribution to baryon number. So here, instead of dimension 5 operators, we consider the dimension 6 operator because the gauge structure, gauge invariance of the Higgs sector in standard model. But the idea is basically the same. So by having some coherent field configuration, spontaneously breaks the range of symmetry, and in turn, it induces the effective chemical potential between particle and antiparticle. And as you can see in these plots, you can see only during the reheating stages, the chemical potential became suddenly large and decays very quickly. So to calculate the final relic of retinal symmetry, we have to determine the reheating temperature. And as I explained in the introduction, this is very non-trivial job. And sometimes it's very complicated. But fortunately, there exists a consistent relation between the reheating temperatures and equation of states and the evolving number of the reheating. And more importantly, we found that what we need actually is not solely a reheating temperature, but a combination of the reheating temperature and the scale factor, evolving number during the reheating. So this A times T turns out to be independent to the equation of states. And for the inflation cases, it has a explicit relation between NS and NS parameters. So by having some constraints from the Planck for NSA parameter, we could determine the favorisms of this rescaled reheating temperature T tilde to be 10 to the 15 GeV to 15 18 GeV. So please note that this is not a pure reheating temperature, but enhanced with the scale factor during the reheating. So to calculate the neutrino production from this retinal number violation, we have to calculate the Bohr coefficients, as I explained in the introduction. So here we can calculate the particle production, neutrino, from time-dependent classical background of Higgs. And this is seemingly very complicated, but yeah, just note that this really shows manifest helicity dependence S here. So depending on S to be plus minus 1, the evolution of beta coefficients is different. And also, the time dependence of neutrino mass, M prime, denoted by M prime, is also essential. And this feature is given by this Higgs, because we are considering the Higgs inflation. And yeah, by having these beta coefficients, we can calculate the number density of the lepton asymmetry, and final lepton asymmetry is obtained by dividing the temperature cube here. And we assume that the final variance symmetry is accomplished by Spalman effects from this net lepton number. Yes, this is the plots for generation of the lepton symmetry. So here, as you can see, for each mose, the net lepton number is generated within a few oscillation, within 5 oscillations. So as I said, even if the rating stages are in general very complicated and there are lots of things we have to consider, but lepton symmetry is insensitive to this detailed of rating history. And as you also can see, for like a purple line, for a large momentum modes, the number density of neutrino is first, so it does not contribute to net lepton number symmetry much. So we have no unitarity violation in this consideration. So this is the results. So by having some Spalman effects, net symmetry is transit to variant number with some factor order of 1/3. And by assuming some reasonable parameters for lambda and psi, and as I said, we have some favorisms of cascade latent temperature. So by assuming some this symmetry, we found that even such a minimal case is enough to generate enough number of variant number to explain the current relic observed in calculated from the BVN and CMB. So this is the summary of part 2. So here we calculated the intrinsic amount of variant symmetry from Higgs inflation within the EFT point of view. So here we consider the Planck suppressed and symmetry break operators. So please note that we do not have any CP violation, explicit CP violation. And this, even if this is just a proposed model, but it also shares some common feature of the inflation. So like a CPT, spontaneous CPT breaking. So it may be also applied to other classes of inflation model, even if the detail depends on the in single field model, minimal symmetry already explained current observation with a high latent temperature, even with a high latent temperature to be 8 times T to be 10 to the 15 to 15, 18 GeV. So yeah, let me conclude. So in part 1, I concentrated on the practical aspects of the rating. So in this precision era of cosmology, it is desired to have a precise theoretical understanding of observation, including the effects of the rating as well. And in part 2, I discussed about some conceptual aspects. There may be potentially very rich phenomenology of rating. And as an example, I chose an example of possible connection to BSM physics, baryogenesis from the rating was discussed. So I want to emphasize that future observational prospects are very promising. So yeah, let's stay tuned. And that's it for me. Yeah, thank you.
Thank you very much, Songmo. Is there any questions or comments?
Can I have a question?
Yeah, sure.
So I couldn't catch the point how the rating states motivate the NSR clause. Please explain once more.
Could you say that again, please?
So how, please explain once more how this page.
Oh yeah.
I mean, please, can you please explain once more? I mean, I couldn't catch the point how this rating stage can modify the
I see.
NSR plot?
So for example, in this non-minimal coupling cases, the values of slower parameters with a large non-minimal coupling is given by 1 over nk square, or determines by these values of nk here. But by having some prolonged range of and reheating, it starts to depart from 60 folding. So in sometimes, by having some finite number of and reheating, we do not have actually the 60 folding. So by having some, once we have some like a 20 folding during the reheating, sometimes 50 folding of the 50 folding during the inflation is enough to explain the to make a CMB pivot scale. So this is one way to understand how reheating changes the predictions of inflationary predictions. And in this formula, and but
how much we can take? I mean, how large we can take n reheating? I mean, normally, how to say?
So that's why usually we take this 50 to 60 folding.
Yeah,
this is the usual values. So what I found is that in these Palatini cases, it is rather different. So in this Cauchy regime, it became smaller than 50 even. So that's why it really departs from the usual expectations for NS values from 60 by 60 folding. So once you assume the 60 folding for these Palatini cases, it should give like 0.965, well within this Planck measurements. But by considering reheating cases, it has a real, okay. So coming back to Palatini cases, at the end of the inflation, the energy scale of the inflation is very, very low than usual cases. So it has also gives some finite values. So it makes the required values for nk to be smaller than 50. So and it really gives a large departure from the usual expected values of NS for Palatini case.
Okay, thank you.
Yeah.
One more. I have one more question. That so you said you consider general cases, but I think you only consider the power law cases, both of the potential and the non-minimal coupling to the gravity.
Right.
So can we have? So my first question is that the power of K and V can be different, and one more question is that can I have the another form of the K or V? No, not K, just maybe.
Yeah, in principle, yes. So so for the ratio between V and K, as I shows in this slides, to guarantee the asymptotically flat potential, we have some specific condition. I mean, V and K should be related at large field values. That's why I only consider these specific choices of K and V. And in general, you can have a different form of K and V, but it doesn't show any asymptotically flat potential, and it will fail to explain these Planck measurements in general. So,
but yeah, so I mean, so if we do not guarantee the flat potential, there will be some kind of hilltop inflation.
Right.
And if the, as you said, reheating. Reheating modify this NSR, then it might also can explain
Right.
observational.
I completely agree with your statements that you can think of other choices of K and V, and it will correspond to other classes of model. And that's why I claim that it is a quite model independent part, even if I consider some specific choices of V and K, it still corresponds to a general classes of models. And as you said, we sometimes assuming different types of case, it will correspond to K-type inflation and to other inflationary models. And we can also draw the same similar. We can also do the similar jobs for each mode, each K and V. But here I only consider these types of potential which shows this alpha objector behavior, basically. So here we concentrated on this alpha objector behavior.
I see. Thank you very much.
Yeah, thank you.
Thank you. And any other further questions or comment?
I have one general question, if I may. So, it seems like you work on the non-minimal coupling gravity with what Einstein gravity can predict, right? NS and R, they're all standard calculation that people do. Is there anything that is specific to this non-minimal coupling?
Any
specific prediction due to the change of gravity? For example, it is a prediction of Einstein gravity that gravitational wave only has two polarization modes. That's just an example. And if you modify gravity sector, then you can have, say, scalar type and vector type polarization of gravitational waves. And is there that kind of like outside of box kind of prediction from this non-minimal coupled gravity?
It's very hard to have such a kind of smoking gun signatures from the non-minimal coupling, because actually by going to the Einstein frame, which is gives an equivalent description, actually we have equivalent theory of Einstein gravity plus non-renormalizable series of some scalar sector.
Right, there, if you go to Einstein frame, then you modify this square root of minus g with some conformal factor that can induce coupling between, or that can induce a time varying fundamental constants, right? You can also think of some consequence of those.
So by having some these redefinitions of.
Right. What I mean is specifically you have omega multiplied to action, and then that omega will appear any interacting particle around them.
Actually, I do not know any specific examples of having some solid predictions from this non-minimal coupling. But I
was just wondering if people are thinking of those kind of direction, because the NS and R, that's common for all. That was motivated from the Einstein gravity. And if you have this other type of starting point, then you may have something.
Okay, specific. So actually we can divide two parts. So in gravity, modifications of gravity parts or equivalent to the scalar sector. So in gravity part, it is very hard because the coupling is too small to see. And even if we have gravitational waves, this will be equivalent. Gravitational wave theory will be equivalent. So the reason we see some effects are due to we believe that this predictions for NSN are coming from this modified sector, scalar sector. So it should involve some modification of this scalar sector. I mean, all predictions or modifications of the prediction should come from this modified scalar sector rather than this gravity sector, I guess. But I have to think more. Let's discuss later. Yeah, I will have to look for more literature.
Yeah, indeed, this non-minimal coupling modified the scalar sector, actually, because we can always recover the gravity, Einstein gravity at the end. However, things can be more interesting if we consider double field or triple field, which have non-minimal couplings. In that case, we cannot really recover the Einstein frame in an easy way. So, for instance, we can imagine non-Gaussianity can be induced from those kind of non-minimal couplings. In this talk, Sungmook more focused on the single field extension.
Yeah, right.
Yeah. So, and for instance, we can also include R squared term.
Yeah, right.
Yeah. In that case, we have additional degree of freedom called scalaron, and phenomenology can be more interesting in a sense. Yeah, we can discuss more later.
Right. But in that case, is actually additional degree of freedom is coming from R scale and higher order of R term, not purely from the non-minimal coupling. So yeah, actually we have to discuss more the case.
Okay, any further questions or comment? Okay, I see no more questions. And let's thanks to Sungmook again. Thank you very much.